Hello, this is Physics 2212, Lab 5, Magnetic Braking with Faraday. My name is Michael Machiraju. So, an introduction to this lab. The purpose of this lab is to observe how much time it takes for a magnet to fall through a tube of aluminum foil, acting as a conductive tube. This data will be compared to a computational model developed by myself on GlowScript using the starter code for this lab. Some preview of the results. It took the magnet 1.15 seconds on average to go through the tube experimentally, and I modeled 1.55 seconds through the GlowScript model. Some assumptions are that I ignored air resistance on a moving object. I assumed the only forces acting on the magnet are the magnetic force and force of gravity, and I assumed that the aluminum foil is a conductive tube that acts like a dipole. Some key ideas: you have Faraday and Lenz's law, which is this equation right here. And of course, we have Newton's second law, which is F equals ma. Of course, you can always use the position and velocity update versions of Newton's second law. So the experimental design. The North Pole is assigned to a bar magnet using the magnetometer app on my phone. One person holds the aluminum foil tube, another holds the magnet above the tube. The bar magnet is dropped through the tube 5 times. Here you can see the different trials that I did. It averaged to 1.15 seconds. Here is some initial conditions. The system is the bar magnet and tube of aluminum foil. The surroundings are the rest of the Earth. Here is a checkpoint. Why can't we use a ferrous tube, for example, a steel pipe? Ferrous tubes contain iron, which means the tube could be used as an induced magnet, which would interrupt the bar magnet's fall. How does the time compare to the bar magnet in free fall? A bar magnet in free fall would fall much faster than through the aluminum tube. And just going back to the experimental design, just so I mentioned, the initial conditions of the system are that the bar magnet is held above the aluminum tube with the North Pole facing down. So here's the coding of a model. So step 1 of the code was to create the bar magnet and tube objects. Step 2 was to create a function to calculate the magnetic field of the bar magnet. Step 3 was a function to calculate magnetic flux. Step 4 is to calculate the current in the ring. Step 5, calculate the B field at each ring. Step 6 is to calculate the magnetic force on the magnet. Step 7, calculate the net force on the magnet. And step 8 is to update the magnet's velocity and position. And so here you can see snapshots of different parts of the code. These formulas that, for example, this was used to in the function of the dipole, this B. And this was the mass of the magnet, which was 0.025, and this is the magnitude of the magnetic dipole moment from lab 3, which I got as 2.3. And so the result from the code was, or the model was 1.55 seconds for how fast the magnet would fall through a tube of aluminum foil of the dimensions that I specified before. So here we conclude. The computational model was moderately different from the measured value in real life. Some big error that occurred was that air resistance was not included in any calculations. This could have altered the result from the computational model. What if the resistivity of the conductor were reduced as close as possible to 0? How would the dynamics of the falling magnet change? The magnetic force would match the magnitude of gravitational force, which would cancel the two forces and essentially suspend the magnet in the pipe. What if holes or slots were cut into the tube? How would this affect the ring currents in your model? The ring currents would be disrupted and the magnet would fall faster since the magnetic force would not be as strong. And that is Lab 5.